Okay, ladies and gentlemen, welcome to the lecture series on atomic absorption and atomic emission spectroscopy. If you are watching this video lecture series, you are probably one of two groups of people. Either one, you're a current student that's in our program, and you're watching these videos because they are a supplement to the course that you're currently taking with us in our CTC 240 instrumentation class. Or second, you're a group of students, probably from high school, that's watching this series of videos in preparation of the Chemtechathon competition that we are sponsoring for this particular year. Whichever group of students you are, we welcome you to the lecture series, and this video segment is going to be, or series, is going to be broken down into a couple of pieces. Number one, we're going to talk about the history of the atomic absorption and atomic emission instrument. We're going to give you a little bit of background about how all of this got started and the people that were involved in allowing this creation to blossom really over the past 50 or 60 years. Number two, we're going to talk a little bit about the theory. So why does the machine work? How does the machine work? What happens to the samples when I put them into the machine? And why do I get a signal from the software or computer that I'm using that's hooked up to the instrument? Number three, we're going to talk about the pieces and parts. So what are the major pieces and parts of the instrument that allows it to do its job? And what's the purpose of them? Do they come with proper or fancy names that I should be aware of? And what happens when one of those malfunctions? How can I fix the problem or troubleshoot the machine in order to get it to do what I need it to do? Number four, after the parts, we're then going to take a look at software. So now that we've kind of led up to the point of we understand why the machine is giving me some data and where that data is coming from, what do I do with the data? So software is going to be involved in that. We're going to take a look at the computer software that's used to make the machine work and some of the various tabs or areas that some people overlook because they don't quite understand what they need to do with a first round of us describing it. So you're going to get a series of steps as far as setting the software up the proper way. And then finally, we're going to take a look at analysis. So once I understand the software, I'll get data, and then what do I need to do with that data as far as spreadsheets go and calculations go. So there's kind of the streamline of the atomic absorption and atomic emission instrument. And we're just going to kind of slowly work ourselves through this entire set. We're not going to rush it because we don't want to take anything for granted. And if it's something that you know already, then good for you. Chances are, though, somebody might not know the same material that you do. So that's why we're not going to take anything for granted along the series of videos. And yeah, that means there's going to be a lot more videos for you to watch, but we would rather be safe than sorry. So again, welcome to the lecture video on atomic absorption and atomic emission. What you're seeing on your screen right now is a picture of the AA or AE instrument that we have in our laboratory. The AA, atomic absorption or atomic emission spectrometer, will come in all forms and all sizes. And you know, these things are like TVs. They have different manufacturers. They might come in different sizes, but a TV is a TV and it all does the same job. The same thing is going to happen to our atomic absorption spectrometer or atomic emission spectrometer. They might be a little bit bigger, they might be a little smaller. The front of them might look a little different. However, they all do the same job, no matter what manufacturer you order them from. So this is a picture of the machine that we have in our laboratory right now. The difference is that up here at the very top left-hand side, the instrumentation manufacturer here is Agilent. And Agilent is a major instrumentation supplier. Agilent is probably one of the largest instrumentation suppliers that are out there. So Agilent really finds its home in the HPLC world. That is another instrument that you'll learn about on a different day, but that's kind of where they're known, and that's how they got their footing in the door. A couple of years ago, we're talking about the mid 2000s to late 2000s. Agilent decides to buy the company Varian. And Varian was getting to be known in their AA world. And Agilent was very jealous of that possibility. So what they did is that they made Varian an offer to buy out their company. And they began a merger between the two. And this allowed Agilent to continue to be stellar in the HPLC market, but it also provided Agilent now an avenue to go in and really get some good equipment and instrumentation in the spectroscopy world, specifically within atomic absorption and atomic emission. Varian actually had a base in Raleigh, North Carolina. So very often we could go up to the Varian headquarters. I wouldn't call it headquarters, but at least in our region it was. We could go up to their site and they would provide us a tour and they would tell us about all of the equipment that they had and show us working in a laboratory. And it was very nice for students at the time. However, Agilent decided to buy them out, and no longer are they Varian anymore, but now they are an Agilent company. So the Varian logo would be stamped right here in the top left-hand corner, and now that, of course, has just been removed, and the Agilent logo has been put on instead. The machine itself is identical. They didn't really change anything at all to it. So this was kind of a turnkey business that Agilent decided to purchase. Okay, so Agilent, of course, is not the first manufacturer of an AA. Or Varian was not the first manufacturer of an AA. The history of AA actually goes back quite some time. And we can actually go back to the years of 1600 for this machine. And for some of you, that might seem like a very long time ago, and in actuality, it is, especially in a science course and especially when it's chemistry related. However, the theory of spectroscopy can go back even hundreds of years before that, but we're only focused on atomic absorption here and atomic emission. So we're not going to go back any further. So one of the first people to study the field of what I would call atomic absorption or emission at the time is a guy, and his name is called William Hyde Wollaston. And he was born in around 1650, and he passed away in around 1720, somewhere in there. And Wollaston is one of the first scientists to actually be given credit or a step in the proper direction for atomic absorption and atomic emission. So we're going to say he was the first. All right. So what he did is that he took a prism, and with the prism, we know now if we shine light through a prism, that light will be broken up into its individual components. So we have red, orange, yellow, green, blue, indigo, and violet. All right, these are the colors of the rainbow that we call Roy G. Biv. Okay, so he was, of course, not the first person to know about the object of a prism. That was years ago by other previous scientists that were working in a laboratory. But he took this concept another step further. And if all light is made up of red, orange, yellow, green, blue, indigo, and violet, Roy G. Biv colors, then this meant that it should look like a continuous spectrum. All right? That means that all of these colors should basically bleed into one another. It should go from red to orange with no breaks, with no other colors in the middle. The red would fade into the orange would fade into the yellow would fade into the green, and it would be a very smooth, continuous process along the course of the color spectrum. But in 1802, not 1802, 1702, he made a closer measurement. William Hyde Wollaston was a person that looked at the stars. He loved the solar system. And during that time, because prisms were already around, what he discovered is that there would be what we would call a spectrum with all of the colors in it, all the way down. Roy G. Biv. And while he was looking at the sun's rays, again, the sun rays should be like natural light. It should be going through a prism, and you could separate them into the individual components with no dark lines at all. What he discovered was that there's areas of the spectrum that basically were blank. They were dark lines, and they had no color associated with them in certain particular spots. But he didn't really try to explain why. He just said, this is something that I observed. While looking at the sunlight, I'm looking at the red, orange, yellow, green, blue, indigo, violet a little closer. And what I'm finding out is that there's dark areas where there's actually no color at all. So maybe in the red region, a lot of the colors were present. But in the red area, there would be a very small but significant dark band with no light coming through at all. Well, again, he only reported it. There were areas like this in red, areas in orange, areas in the yellow, areas in the green, blue, and indigo and violet. These dark areas were showing up everywhere. But the majority of the colors were there. The majority of the spectrum was present and represented. For the most part, they did bleed into one into the other, so it was thought to be no big deal. All right, so here is a picture of Mr. Wollaston, and then here is a picture of the spectrum that we're talking about. So if you look at the colors, you see the red, orange, yellow, rainbow colors that are present. However, every now and then you see a dark line. It's like a missing piece. No color is present. And these areas or these bands that are completely dark, this is going to be picked up by someone else. Wollaston didn't really do anything with it. He only reported it. And he said, this is what I'm seeing. So finally, later, after these dark lines were reported, we get another person to step into the picture and pick up where Wollaston leaves off. And that person we'll talk about in the next video. So come back, take a couple of minutes if you have to, get yourself together, get a good sheet of notebook paper and a pencil because you'll be taking a lot of notes, and then we will pick up on what we call Fraunhofer lines.